So here is where we left off yesterday. Let's take a look at this informal definition here. And then we're going to go a little further forward with this whole limit thing, right? So we talked about limits. Here's one way to define it's one expression of an informal definition of a limit. So why don't you click them all closed, take a look up here. Let f of x be a function defined at all values in an open interval containing a. Isn't that kind of where we left off, defining what you guys reminding me what an open interval is? Yeah, how does that work? Open interval versus closed interval. What are the differences? Okay, what's not included? You're right. The endpoints. The endpoints. Yeah, exactly. So we would say, like, for example, here's an open interval, or here's a closed interval. Closed interval would look like from 0 to 5, for example, which on a number line, if that's 0 and that's 5, we would get closed endpoints, right? Open interval would have open endpoints, so it's not including the endpoints. So then going back to our definition, let f of x be a function defined at all values in an open interval containing a, so a is our number we're referring to, with the possible exception of a itself. So it doesn't necessarily have to be defined at a, but everywhere surrounding a, in an interval surrounding a, it does need to be defined. Okay, does that make sense? Okay, so these are the criteria that we have to meet for this definition. Okay. And let L be a real number. So L is just some number. If all values of the function f of x approach the real number L as the values of x approach the number a, but remember, x doesn't actually ever get to a, right? As they approach the number a, then we say that the limit of f of x as x approaches a is L, and that's how we'd write it. Okay, you get the idea? So for this to work, as the ant gets closer to a, the function gets closer to L. Okay, so that's kind of what we discussed yesterday. So how about this guy? Just a little review from yesterday. Here's a graph. We've got the function g of x here. What is the limit of g of x as x approaches -1? It's 3. Yeah, what is the value? What is this instead? Tell me, what is g of -1 equal to? 4. Because that is the actual value the function has there. But the value of the limit is 3. Because that's where the ant thinks he's going to step. Uh-oh, what happened here? I just want that guy. There we go. Okay. How about, what's this about? I can't remember. Oh, just an explanation. Okay, you guys got it. Okay. So next step for us, we defined this idea of a limit. Now we're going to get more specific. Sometimes it's helpful to consider limits from the left or the right of a value specifically. So there's a direction attached to this. So we need to define what we call one-sided limits. There's 2 types. So let's look at the one in red here first. The limit from the left. Limit from the left looks like this. Okay. The limit of f of x as x approaches a. What do you think that negative superscript means? From the negative side, from the negative direction, right? So as an ant is walking from the left towards the value x equals a, if the ant anticipates stepping on a y value of L, then that's our one-sided limit, okay? And then the other one that you would talk about is, same thing, but from the right. Okay, so the plus sign in the superscript means that x is approaching a from the positive direction. Okay, from positive infinity, sometimes people say. Okay, and this is what we call one-sided limit. So the one-sided limit of a function as x approaches the value a from the left corresponds to the y value on which the ants would anticipate stepping when they approach a. And then same thing for from the right. Okay, why is this important? Well, you'll see. We're going to look at lots of examples. But one thing this does for us is it tightens up our definition of a regular kind of a two-sided limit. You know, what we were calling a limit yesterday, now we're going to call a two-sided limit. So let f of x be a function defined at all values in an open interval containing a except possibly at a itself, and let L be a real number. Then the limit of f of x as x approaches a is equal to L if and only if the limit of f of x as x approaches a from the left is equal to L, and the limit of f of x as x approaches a from the right is L. In other words, what's that telling us about two ants approaching a from opposite sides? In order for the limit to exist, what has to happen with those two ants? They have to anticipate stepping on the same place, right? If they disagree, if they both anticipate stepping on different places, then the two-sided limit doesn't exist, okay? Because both of the one-sided limits have to exist and agree for the two-sided limit to exist. That's a two-sided limit. Anytime there is not a plus or a minus there, it's automatically it's a two-sided limit. You only get that superscript if it goes with a one-sided limit. Okay, give me thumbs. How we doing so far on this? That all making sense? Question? Oh, okay. Okay, gotcha. Gotcha. And I didn't get the, I did all my Algebra 2 classes yesterday, but these will be up today on Google Classroom. Promise you. I'll get all the notes will be up there and all the videos. You'll have links to them. Okay. You good? Okay. Questions? Everybody's good with this concept? Don't hesitate to ask. If you have a question, other people do too. So please ask. So then, you know, we've seen stuff like this. We could look at it with a little different perspective now. If we're trying to go back and look at this example from the other day, well, what's going on here? As we approach, as x approaches 1 from the left, you can see that the output values, the values of f of x, are gradually increasing upwards towards 3. As we approach 1 from the right, the values of f of x are decreasing towards 3, and they converge on 3. The two one-sided limits agree, so the limit works. Okay? All right. So let's look at some examples here. Okay, yeah, we want to just practice a little bit. Why don't you guys bust out your Chromebooks real quick and do this. I want you to try to evaluate this limit graphically. And I'm going to show you how to do it on your TI-84s also. Okay, so the limit of sine x over x as x approaches 0. Okay, what mode do you need to be in on this, by the way? When you're dealing with trig functions, what mode are we almost always going to be in? Radians, yeah. Only if we specify otherwise would we be in degrees, right? Radians, and there's a reason for that we'll talk about. Radians have meaning. Degrees are totally arbitrary and made up. I mean, really, if you think about it, why are there 360 degrees in a circle? What's the reason for that? Why couldn't there be? There could be 100 degrees, or there could be 1,000 degrees. It doesn't make a. Somebody just arbitrarily said 360. Why'd they pick 360? Only reason? It's a highly divisible number. Yeah, it's divisible by lots of things, and so it's easy to break it into fractions of one complete journey around a circle. That's it. Okay, that's the only reason. We'll talk more about that later. Try this. So I want you guys to use Desmos to try to tell me what this limit is. What's the limit of sine x over x as x approaches 0? And right now, remember, the only methods we have for evaluating limits are we can evaluate them using, graphically, using graphs, or we could use tables. Let's do this one graphically. Oh, what happened there? Huh. Okay, so everybody got something probably kind of like that, right? When you graph that function. So what are some things we can do here? I mean, I know we've talked a lot about this in Algebra 2, but let's again, we want to be able to use these graphical devices, these technology tools to the best of our to best advantage here, right? So one thing we always want to do is we kind of want to stretch things out so we can see the graph better. Well, this function looks like it's capped at 1, right? So why don't we go over to the graph settings if we want to make this look better, and on the y-axis, instead of going from negative 5.274 to positive 5 point something, why don't we just go from something like negative 1.5 to positive 1.5 in steps of 0.5, something like that. That helps, right? Okay, now what? So what can we do? Well, one thing we can do here, if we're just trying to get an answer, let's just drag a point along this thing, and what's the trend? What value is that approaching, the y value? It looks like to 3 places it actually shows you 1 on here, right? So it's getting closer and closer and closer to 1. We can just see from the graph. Okay, another thing you could do if you wanted to is you could just identify a point that's really, really close. You could pick a point very close to x equals 0, right? So we would do that by just saying something like, oh, I don't know, like 0.0001, comma, f of 0.0001. And what's it tell us? If we label the value there, yeah, look at that. I mean, it rounds to 0.1 just because Desmos doesn't keep that many decimal places, right? Uh, how could I do this in a way where I could vary? Like I picked a specific point. I want you guys to get good at using Desmos because you're going to use Desmos and things like it in college a lot. How could I make this a little more versatile? Instead of picking a specific point, what could I do here? I did something like this yesterday. This is a little bit of it's coding practice too. I don't want to limit myself to just picking that one x value. I want to be able to pick any x value I want without having to retype it every time. Okay, I could do something like put in a. Yeah. Why don't I just I'll put in a value a and f of a, and then it even prompts me. It says, do you want to add a slider? Yeah. If I click on the a, it gives me a value for a slider, and I can either slide this thing, or even better, I can just go up here and type in a value like negative 0.01. Look what it does. It puts me at that spot because I've written my ordered pair. I've defined it in terms of a. Everybody see that? Okay, this is good mathematical thinking that relates to the way you think when you code stuff too. We don't have really opportunities at our school, unfortunately, for doing any kind of serious coding, and that's a skill I would encourage you guys to try to. I know you're super busy, but if you can find any time at all to just look at Khan Academy, mess around in some like Scratch or some of these online coding environments, your time is precious and you may not have a lot of time to do that. But if not now, over the summer or something, that would be a really good thing to do before you go to college. Okay, how about on the, take a picture for our notes, how about? And then how would we do this on our TI-84s? Because you guys are going to be needing your TI-84s on the AP test if you're taking the AP test, and you can use it on the SAT test. So the more you know, better. Oh, what happened? There it is. Okay. Just throw those on there for our notes. Okay, how could we do this? Well, I've got my emulator here somewhere. I think I got that installed. Man, I don't know. There it is. Okay, we can do almost the same thing, and I'll be really quick with this. I want to get going, but I do want to make sure you're comfortable with technology here. Let's see. I want to just do. No, I want to do. Yeah. Ah, come on. Okay, so what I'm gonna separate this so the screen is sort of enlarged, so you can see this a little bit better. Same idea though. So let's delete everything, quit. So I'm gonna go into graph. You guys know this. You go to y equals. Let's let's make sure we're in the right mode. Are we in radians mode? Yes, we are. Okay. So y equals. I'm going to use my little shortcut for a fraction bar, and I'll do sine x divided by x. And I'm going to start off going, okay, on zoom. What are our options on zoom? Usually we do zoom fit, right? Which takes us from -10 to 10. Zoom 0, that's what we did in algebra 2, right? Zoom 0 goes -10 to 10 on both x and y. Do you see possibly a better one here to start with? Or we went zoom standard, sorry. We always went zoom standard, which is negative. If I do that, if I do zoom 6, it does that. -10 to +10 on both the x and y axes. You see a better zoom? Let's try trig. Look what happens with trig. It's a little bit better. If you look at the size of the window then, look what it's doing. It's going from, well, that's kind of a weird one. It's going from a little bit more than, it's like 1 1/4 pi or something. It makes the scale on the y-axis a little bit more expanded though. And we could even tweak that more. We could come down here and go from, instead of going from -4 to 4 vertically on the y-axis, why not just go from like -2 to 2? Looks better, okay? And then we can do the equivalent thing that we just did on Desmos by just tracing, right? If I just trace on this thing and just trace to the right or the left, it's telling me the x and y coordinates down here at the bottom. So just by tracing along, we can see that those y values are climbing towards 1, aren't they? From the left and the right, okay? Do you guys remember from algebra 2? Let's see, hopefully you were doing a lot of this last year too. Do you remember how you can use trace to go to a specific x value and y value on the function? Putting you on the spot here. All you got to do, it's real simple. Okay, it's not even that complicated. All you have to do is hit the trace button and then type an x value. So if I type 0.0001 and hit enter down here, look what it does. It puts me at that place, 1 times 10 to the -4. and y is equal to 1. Okay, everybody see that? So you can specify values. You don't even have to just trace along with the arrows. You can type in an x value after you hit trace and then hit enter, and it goes to that point. Here, I'll do it one more time. If I do trace 0.5, it'd be more obvious. Look what it does. It puts me at that point right there with an x coordinate of 0.5 and a y coordinate of that. 0.95, blah, blah, blah. Okay? Give me thumbs. That making sense? Okay, that's a graphical tool for doing all this stuff. Okay. How about I'm going to put this picture on here for you. Okay, how about using a table? So how could we use use a table to find the value of a limit? You can actually do this on, we'll do this on both again. Tell you what, let's just use the same stuff we had before too. I want to speed this up a little bit. If I go back to here, right, I defined this function. I don't need any of this stuff now. If I'm going to make a table, how did I do that yesterday? I define the function and what do I do? Okay, good. Yeah, I click the gear for settings, click the table icon, create a table, and we're good. And then we can just specify where we want that thing, what we want that thing to do. So we want to stay pretty close to 0. So what if we did something like we went from negative 0.1, negative 0.09, and then we just follow that trend, right? We're just climbing up towards 0 and beyond. And we can see that those values are converging on 1 in the middle. Okay, good. Okay, let's get that. I'm going to put these pictures, some of these on the next page. I'll just add a page. So they'll be on the PDF when you want to look at it. And then how could we do this using our calculators? Okay, now this one I'm gonna have to think about a little bit. I haven't done this in a while. So we're gonna clear, and we're gonna go up to, let's see. So I'm gonna go to table set. I'm gonna go second, F2. So I want my table to start at, let's go at negative 0.1. Okay, what do I want my steps to be on the table? Let's do what we just did. How big were my steps? 100th, okay. So we'll go down, we want our steps to be of width 0.01, right? So we're gonna, starting at negative 0.1, we're gonna inch towards 0 in that size increment. And now for my independent, let's see what happens if we leave it like this. So now if I go second table, look what it does. Okay, pretty handy. Same kind of thing, right? If I scroll down, it's just showing me this kind of thing, right? The left and the right are converging on 1. Okay. There's something else you can do here that's pretty handy. If you go back to table set, I really like this. If you go to table set, so second, what happens if you go down and instead of making the independent variable, the values of auto based on what I just said, and now if I go to the table, I can type in any value I want to. That's kind of nice, right? So I can try like negative 0.1. Okay. Uh-oh. What I do? Fine. Okay, and look at so I think, oh, okay, well, that's pretty good. I want to get closer. So then I can just try, pick any value I want. 0, negative 0.001, let's try. Okay, and it gets me to 1. Then I could try something on the positive side, 0.001. And rounded to 4 places, it's 1. Okay, make sense? Okay, it'll be all in video too if you want to come back and review this. All right, moving on. So let's talk about this now. Let's take this problem in terms of one-sided and two-sided limits. Let's discuss this function here. I'm showing you the graph. We don't know what the function is, but we can see the graph, right? What can you tell me about the limit from the left? What's it equal to? Okay, everybody agree? So if I take the limit from the left, the limit of, it's g of x, it looks like. I could write the whole function down, but I'm not going to. I'm just going to write g of x. That's the graph. As x approaches, what would I write next there? Okay, that means from the left, right? As we approach from the left, the limit is equal to negative 1. And we see that right there. Okay, give me thumbs. Does that make sense? Okay, how would I write the limit from the right? Limit of, tell me what to write here. You guys got to get used to this. Limit of g of x 2 from the right, okay, so 2 positive, is equal to 1. And we know that because of that open endpoint right there. And can't step on it, but that's where he thinks he's going to step. Okay, so then let's combine those. The limit of g of x as x approaches 2 is what? Seeing some quizzical looks for good reason. What do you think about the answer to that? What is that limit? There isn't. What's that stand for? Does not exist. DNE. Okay, make sense? Oh, that doesn't look like an E, does it? There's an E. Must have run out of ink in my finger on that one. Okay, good. And it's because the limits don't agree from the left and the right. Right, remember that for the two-sided limit to exist, the one-sided limits have to exist, which they do, and agree, which they don't. Okay. Then it would have worked. Yep. Then it would have worked. Then the answer would have been negative 1. Yep, exactly. Okay, let's discuss this one. In terms of one-sided limits. Now, the answer to this is this limit does not exist, first of all. It doesn't exist. How come? Because there's no number value. There's no one point the ant is approaching, right? So right up front, all of these no limits exist. But we can say something more about that with one-sided limits. We can be a little more specific. As we approach from the left, even though the limit doesn't exist, we still can say something very powerful about it. the limit of f of x, we'll call this, as x approaches 2 from the left. Yes, it doesn't exist, but what could you say that describes that more powerfully? What does the limit approach? What is the value of the function approach as x approaches 2 from the left? Well, as x approaches 2 from the left, what value is the ant climbing towards? Infinity. Yeah, positive infinity. Okay, even though that infinity is not a number, right? And so that means the limit doesn't exist. There's no number we can write there. That still tells us something really powerful about the behavior, right? So we'd call this an infinite limit. If we had to give this topic a title, we would call it infinite limits. Okay, what is the one-sided limit of this function as x approaches 2 from the right then? What's that equal to? And again, saying equal is kind of a little bit goofy here. I mean, that's not technically equal to, but the limit approaches what value? Infinity. So it doesn't exist, but it's climbing to infinity. And so therefore, what can we say about the two-sided limit? Even though it doesn't exist, it does have a describable behavior here. The two-sided limit of f of x as x approaches 2 is what? Infinity, yeah. Okay, we had consistent behavior from both sides. Okay, that's different from, let me go back for a second. That's different from something like this, for example. Say we had a function that did this. So there's an asymptote, right? What if it did something like that? Now what would the limit from the left be? As we approach 2, limit from the left would be infinity, right? Limit from the right would be negative infinity. And so the two-sided limit, there's nothing we could say about it. We couldn't say infinity, positive or negative infinity, because it's inconsistent. Everybody see that? Okay. Okay, let's practice. Based on that graph, let's just go around and you guys are going to shout out some answers to me. So I want to know the function g is graphed, so g of 1, go. Aubrey, what do you got? G of 1 is g of, this is the graph of g over here. It's this weird piecewise function. You're looking at the all pieces. That's all part of a piecewise function. Right, so G is this whole thing. It has an open endpoint here, then it goes up here. It's all of that stuff combined. Okay, so it's 4. Okay, good. Everybody agree? G of 1 is 4. Yes, yeah. G of x is the whole thing, exactly. Tabri, what do you get for B? What's the limit of G of x as x approaches 1 from the left? As we approach 1 from the left, it's 2. Everybody agree? Okay. I don't need to pick on individual people. You guys can just kind of share the wealth here. How about it? I don't need to call on you. So that one's 2. How about C? Limit of g of x as x approaches 1 from the right. Just show me with fingers. How about that? Because these are all just integers. Everybody just hold up fingers to what's the answer to C going to be? Yeah, good. It's 4, isn't it? Yeah, right? Because as we approach 1 from the right, the ant is walking towards that point. That's the point he anticipates stepping on, right? It's irrelevant that that's where he actually is, okay? So then what is the limit of g of x as x approaches 1? Doesn't exist. How come? Because the one-sided limits don't agree. Ants approaching from the left and the right anticipate stepping on different points. So part D is DNE. Okay, what's G of 3? Show me with your fingers, everybody. What's G of 3? Good. It's 1, right? It's that point right there, isn't it? That's where the ant will stand when he steps on an x value of 3. What's the limit of G of x as x approaches G from the left? Show me with fingers. The limit of G of x as x approaches 3 from the left. Okay. No, from the, there you go. Good, okay. Good, good, good. 4, because he's approaching that point right there, isn't he? Okay. So how about the limit of G of x as x approaches 3 from the right? As x approaches 3 from the right. Good, 1. So the two-sided limit wouldn't exist, right? Okay, how about G of 4? 2. This one isn't up here, but what's the limit of G of x as x approaches 4 from the left? Good, 2. What's the one-sided limit of G of x as x approaches 4 from the right? Good. What's the two-sided limit of G of x as x approaches 4? Good, 2. They agreed. They existed and they agreed, right? Good. Ants from both sides anticipated stepping on the same point. Okay, so now let's look at some specific behaviors now where limits fail to exist. And we've seen these things, most of these things already. One place where limits failed to exist that we looked at a little bit ago was a place where there was a gap in the function. So different behavior from the left and the right, which a lot of times we just call a break in the function or a gap in the function. Guaranteed limits have to, at the place where the function breaks, that limit does not exist. Okay? What else did we find? We found that if there was asymptotic behavior, unbounded behavior, the limit doesn't exist. Now we can still be descriptive and maybe throw in some infinities sometimes, but the limit doesn't exist. Okay? And then the third kind, I want to do a little exploration here. We're going to have a little fun. When are we out of here? I got to remember the schedule here. 20? Oh, so we're not going to probably get through a lot of this, but we'll get through a little bit. Let's take a look. Now, I want you guys to get used to looking at compositions of trig functions. This is a good thing to do. So let's start off by just looking at a sine function. There is a graph of y equals sine theta. Okay, you guys know what a sine function looks like. This wave train. Okay, so let's replace this now. Let's replace this with the sine of the argument of the angle AX. Where A is 1, it looks like that. What's going to happen if I make A a big number like 3? What's going to happen to that? Okay, well, let's try it. Now, A is what's being multiplied by X inside the sine function. Okay, are you thinking of like what happened? What if I put a number out here in front? What if I put 2 out front? That makes it taller, right? That's the amplitude, the number out front. Whoops. So what's it going to do if I multiply the angle by 2 or 3 on the inside? Okay, that's the thing. So is it going to become spread apart or squished together? That's the question. Let's try it. See if we can explain it. If I make this a big number, look what happens. It gets squished together.
It doesn't get any taller.
No, it doesn't get any taller. Just gets squished together. And if I make the number smaller than 1, it gets spread apart. Okay, makes sense? Now, why is that? Let's look at this. If y is equal to the sine of 2 times x, Think about functions as machines. We're going to run out of time in just a second. But the sine function doesn't know where the numbers you're feeding it are coming from. We just give it values and it spits out answers, right? Okay, where are the values coming from? Well, they're coming from the expression 2x. So if I let x equal something like pi fourths, sine isn't going to see pi fourths, it's going to see 2 times that, right? So by the time x goes from 0 up to pi fourths, 2x has gone from 0 up to pi halves. Everybody agree? So putting that 2 in there is really multiplying the rate at which the sine function is seeing angles. You get my point? So it's going to squish those together because the sine function is seeing angles faster. Okay? We'll get back to this one tomorrow.